In this video, we will discuss about the significance of equilibrium constant K and how is it related to the chemical equation. So we know that the equilibrium can be reached from either the reactant side or from the product side. And we write the equilibrium constant K equal concentration of product divided by concentration of reactant. So this is a constant. This is not going to change when the initial concentration of the reactant or products are changed. Then how can you change the K value is only by changing the temperature. So since we are using the concentration in the numerator and in the denominator, so the units will cancel. So we don't use a unit for K. And now the equilibrium constant, how is that going to determine whether it is favoring the products or reactants is depends on the size of K. What is that means is, suppose you have a value for the product, the molarity, we can say 10, and for the reactant it is 5. So we know the K will be 2. That means it is greater than 1. K value is greater than 1. So that means when you look at the numbers, you can see that we have more products here. And if it is reverse, that means if we have products 5 and reactants 10, we know the equilibrium constant value is going to be 0.5, which is less than 1. That means we have more reactants. So this favors, if K value is less than 1, it favors the reactant. If K value is greater than 1, it favors product. But the size does not tell us, it's not going to tell us anything about the speed of the reaction. That means we cannot say how much time it's going to take to reach that equilibrium. It will just tell us whether the equilibrium lies either towards the product side or towards the right side or towards the left side. That's the only thing it will tell us. So that means more products or more reactants is going to be there at equilibrium state. Okay, so to remember that one, what we can actually do is write K value first. And if it is greater than 1, look at that, in which direction it is pointing. It is pointing towards the product side, right? And if K is less than 1, it is pointing towards the reactant side. So if you think that is going to make it easy to remember, just go with that one. That's a shortcut to remember. Let's see these examples. In the first one, it says H2 plus I2 gives 2 Hi. The value of Kc at 450 degrees Celsius is 50. So at equilibrium, what will happen? Let's go ahead and see the K value here given. So the K value is greater than 1. So K value is 50, right, which is greater than 1. So at equilibrium, we will have more product. That means Hi will be more in this case. And in the case of N2 plus O2 gives 2NO, K value is 4.1 times 10 to the power negative 1, negative 31. That means K value is less than 1. This is negative 31, so it is going to be a very small value. So that means what? At equilibrium, we will have only the reactants. So that means it is reactant favored, right? And the top one, the first example is the product favored. And now, what if a chemical reaction is modified? We normally modify the chemical equation in 3 ways. So what will happen to the K value when we modify that? So if we are changing the coefficient, what will happen to the K value is the K value from the original one will be raised to the power of the coefficient. What is that means is, let us take an example here. Suppose we have an equation 2NO2 gives N2O4. We can write the same equation by putting NO2 gives half N2O4. In this case, I just wrote the equation in a different way, but it is chemically equivalent. So there is no difference in the reactant or the product, only the coefficients changed. So how is that equilibrium constant going to change? In this case, suppose the equilibrium constant is K. So for the second equation I wrote, what happened to the equation is I just multiplied that first equation by half. So that means the coefficient 2 divided by 2 will be 1. And here the coefficient is 1. So the coefficient changes to half here. So in that case, what happened for the k value is I had to raise to the original k value to the power half. That means square root of k. Suppose if we are multiplying an equation by 2, and then the original k value will be raised by 2. Suppose the equation is multiplied by 3, and then the original k value should be raised to the power 3. That's what it means. And now, since the equilibrium can be approached from either direction, either reverse, forward and reverse, we can actually write the equilibrium constant, and this magnitude of the equilibrium constant depends on the form of the chemical equation I'm writing. Okay, what that means is, let us take an example. Nitrogen plus hydrogen gives ammonia. I can reverse that equation. So there is a k value here for this equation, and if I'm reversing, 2NH3 gives you N2 plus 3H2. Okay, so in that condition, what will happen is the original k value will be the reciprocal. The new k value will be the reciprocal of the original k value. And now another modification for the equation we normally do is adding different equation to get a specific net equation, correct? So when you add, what happens is, for each equation we will have different k values. So to get the new one, what I will do, I have to multiply the k values. Let's see each one with an example. Okay, in this question we can see an equation which is 2NOCl gives 2NO plus Cl2 at 35 degrees Celsius, Kc equal 1.55 times 10 to the power negative 5. And the question is, calculate the value of K for the reaction 2NO plus Cl2 gives 2NOCl. So what is the change here? You can see that NOCl and NOCl is the reactant, right? And in the new equation, NOCl is the product. So that means we are reversing in the first case. So when we reverse, how can we do that? Let's see. So we are reversing. So when we reverse the original K value, we have, that is Kc is 1.55 times 10 to the power negative 5. So the new K value will be reciprocal. So 1 over Kc. So that means the new K value equal 1 over Kc, that equal 1 divided by 1.55 times 10 to the power negative 5. That equal 1 over 1.55. I am taking that 10 to the power negative 5 from the denominator to the numerator. So it will change to plus 5. And plug in the calculator 1 over 1.55. We can see that that equals 0.645. And I will write that exponent 10 to the power 5. And then scientific notation, move that decimal. That will equal 6.45 times, since I moved one place to the forward, so the exponent will go down by 1, so 10 to the power 4. That's the answer for the first one. And in the second one, what is happening? Calculate the value of K for the reaction. 4NOCl gives 4NO plus 2Cl2. So what's the change we can see? NOCl is the reactant, NOCl is the reactant. But the coefficient is 4 here, coefficient is 2 here. So in B, what we are doing is we are multiplying the equation by 2, correct? That means 2NoCl gives 2NO plus Cl2. We are multiplying that equation by 2 and we are getting 4NoCl gives 4NO plus 2Cl2. The coefficients are multiplied by 2. So what's the rule? So we will get a new K for this equation. So that will be the original K to the power 2. So that equal 1.55 times 10 to the power negative 5 to the power 2, that equal, when you plug it in the calculator, 1.55 times 1.55 will equal 2.40, and negative 5 times 2 will be 5 times 2 is 10, so negative 10. So that's how we are applying those rules in a calculation. And now let us see another example. The following equilibrium concentrations were observed for the Haber process, formation of ammonia from nitrogen and hydrogen at 127 degrees Celsius, and we have the concentrations of the reactants and the product. So first we have to write the balanced chemical equation. N2 plus 3H2 gives 2NH3, and then write the K expression, which is concentration of ammonia to the power 2 divided by concentration of nitrogen times concentration of hydrogen to the power 3. And then we can plug in the concentrations given, and then we can do the calculation. So let us say the calculation, that is 3.1 times 10 to the power negative 2 to the power 2. I am going to expand. You can actually substitute in your plug it in the calculator. So I am just expanding 3.1 times 3.1 times 10 to the power negative 4. Negative 2 times 2 will be negative 4, and divided by 8.5 times 10 to the power negative 1 is 0.85 times 3.1 times 3.1 times 3.1 times 10 to the power negative 9. That will equal 9.61 divided by 25.32, and I'm going to take the exponent separate. Negative 4 and the negative 9 is in the denominator, so I had to take it in the numerator, so we had to subtract. So that will equal 9.61 divided by 25.32 times 10 to the power 5. So that equals 0.379 times 10 to the power 5, and then in the scientific notation, so move that decimal to the right and then the exponent will go down to 1. So the answer will be 3.75 times 10 to the power 4. And now second part, calculate the value of the equilibrium constant at 127 degrees centigrade for the reaction. 2NH3 gives N2 plus 3H2. That means the reaction is reversed. So the new equilibrium constant will be the reciprocal of the original K value, that is 1 divided by 3.8 times 10 to the power 4, that equal 1 divided by 3.8 times, I'm taking that 10 to the power 4 to the numerator, so negative 4, and then 1 over 3.8 will be 0.26, and 10 to the power negative 4. Move the decimal and then you will get 2.6 times 10 to the power negative 5. And C, calculate the value of the equilibrium constant at 127 degrees Celsius. So what happens here is the original equation is multiplied by half. So half N2, 3 divided by 2 H2. So the new equilibrium constant will be original equilibrium constant to the power half. So square root of K. So square root of 3.8 times 10 to the power 4. Square root of 3.8 times 10 to the power 2. So that will be 1.9 times 10 to the power 2. And now pause the video and try this question by yourself to find K3 for this equation from these two equations, and then check your answer. You should have this answer. You have to follow 2 steps to get this answer. So first we multiply the equation 2 by 2 and then add equation 1 and the modified equation. So when you multiply, you will have this equation and the K value will be to the power 2, and you will have K value 10 to the power 6, and 2F minus plus 2H plus will give you 2HF, and then add equation 1 and the modified one. So 2f minus and 2f minus will cancel, and you will get the required equation. And then to find the K3, you just multiply the modified K value and the original K value from the equation 1, and you will get